Remember a long time when I asked you how you could make a better approximation for a function besides just using the tangent line? So we talked about a couple of different ways. You learned about Euler's method, where you start at a point you know and sort of walk along a slope field diagram to approximate a new function. And then we talked about having a function that doesn't just match at the doesn't just match at the y value and match the slope, but would match the function value and the first derivative and the second derivative and keep going. And it turns out that that's exactly what we're going to do in this section. We are going to write what is called a Taylor polynomial, which is a polynomial that approximates a new function. The cool thing about a Taylor polynomial is that it is a power series. It's a constant times the power of x plus a constant times the power of x plus a constant times the next power of x, which makes it a polynomial, which makes it very easy to perform calculus on. So in the last section, we found some of these power series, some of these polynomials, by taking the one fact that we knew from pre-calculus or algebra 2 about how a geometric series converges to 1 over 1 minus x if your first term is 1 and your r is x. And then we did sort of transformations on that one equation to make new functions. So what if you want to write a polynomial to approximate a function that's not anywhere at all related to 1 over 1 minus x? For example, what if you wanted a polynomial to approximate the sine function? How can you transform 1 over 1 minus x into sine? Doesn't happen. So we're going to talk about another way that we can go about constructing that polynomial. And just to prove that it's not going to be too horrible, let's try this out. So we're going to warm up for Taylor's series by making a polynomial. It has, we would say this has degree 4 because the highest exponent on x in our polynomial is going to be 4. And I have these specific behaviors that I want. So I want p of 0 to be 1, p prime of 0 to be 2, p double prime of 0 to be 3, and etc. So notice what happens when I try to make this polynomial. If I want p of 0 to be 1, imagine plugging 0 into this p function. I'm plugging in 0 for x, right? So here, every one of these terms has an x in it. So when I plug in 0, those terms just go to 0. So the only thing that's going to be left is a sub 0. And if I want p of 0 to equal a sub 0, then a sub 0 should equal 1. So I've decided that a0 should equal 1. Okay, so now that one's set. I'm going to try to figure out a sub 1. If I want to be able to plug in 0 to p prime and get 2 as the answer, well, let me start by figuring out p prime. P prime of x is, well, the derivative of a0 is 0. The derivative of a1x is a1 plus, when I take the derivative of a2 times x squared, the 2 comes to the front, 2a to the second, now x to the first. I'm going to keep going. But you could see that when I find p prime of 0, every term that has an x in it is going to turn out to be 0. So for p prime of 0 is just going to equal, all those other terms cancel out. P prime of 0 equals a1. So if p prime of 0 is supposed to be 2, then a1 should equal 2. And maybe you feel like you've got this all figured out and you know the pattern. But let's try the next term. So I might start by finding p prime of x. So I'm going to take the derivative of p prime, which I found the last time around. Well, the second derivative, I'm going to have to take the derivative of that constant, which is just going to go to 0. I'm going to have 2a2 plus, this was 3a3x squared. The 2 is going to come to the front and multiply the 3, so that's going to be 6a3 times x plus dot dot dot, and you can sort of imagine the rest of those terms. When I want to find p double prime of 0, everything that has an x in it is going to go to 0. I'm going to have p double prime of x equals 2a2. And p double prime of 0 is supposed to be 3, so 3 equals 2a2, which means that a2 equals 3 halves. So now when I find p triple prime, I've only got two terms left. P triple prime of x is 6a3 plus 24 a sub 4x. So if p triple prime of 0 is supposed to equal 4, when I plug in 0, that term's going to go to 0. So 4 is going to equal 6a3. So a3 is going to equal 4/6. I'm going to write that down there. A3 is 4/6. I'm not going to simplify just to make a point in a second. And when I want to find p, the fourth derivative of p, sorry, there's no fancy name for it. I guess you could call it p quadruple prime. Probably when you're on your interview to Harvard, you should say the fourth derivative of p. Fourth derivative of p. You could make 4 little quote marks. It's more common to put the Roman numeral 4 in parentheses. So p, fourth derivative of p is 24a4. So if 24a4 is equal to p, the fourth derivative of p, and when I put in 0, I'm supposed to get 5. So that means that 24, oops, I got it backward. 5 is 24a4, so 5/24 is a sub 4. So you'll notice in our final answer, this is a polynomial of degree 4, so x to the fourth is the biggest exponent in my polynomial. The derivatives we wanted show up here, 1, 2, 3, 4, 5. And we might start to wonder, we want to ask this question, where do we think that these numbers, 2, 6, 24, and then could you figure out what the next numbers are? We're going to see where they come from and how that helps us, how the pattern helps us to build other kinds of polynomials in the future.